My name is Anansa Keaton, and I'm a senior at USC studying physics and astronomy. Today I'll be talking about the halo mass function and the ways in which we use statistical surveys and universe simulation to get a better understanding of our universe. For starters, we need to discuss the large-scale structure of our universe. From our perspective on the Earth, when we look into the night sky, our universe seems distinct and full of non-uniform densities of stars and galaxies. In fact, even on the scales of megaparsecs, the universe still looks largely anisotropic. It's only when we look on scales of hundreds of megaparsecs that the universe begins to look uniform, homogeneous, and isotropic. At around 300 megaparsecs, we start to see the connected filaments of the universe. These filaments are connected galaxy clusters and superclusters that formed in the early universe. The picture on the right of the screen shows these filaments, the brighter areas of the picture representing higher densities and clusters, while the darker colors represent lower densities and less clusters. But what can these galaxy clusters tell us? Well, since these galaxy clusters are observable to high redshifts, this means they were one of the first large-scale structures in the universe. These galaxies were observed using the SC effect, where C and B photons are distorted through inverse Compton scattering, meaning photons are given extra energy from collisions from electrons emitting from these galaxy clusters. The way in which these galaxies clustered depends on the power spectrum, mass composition, and the presence of dark matter. Observing these effects of these parameters can give us an insight into the force behind the acceleration of our universe, the evolution of our universe, or can tell us whether or not our methods of observation are altered by the presence of gravity on large scales. But what do we do with these galaxy surveys? After taking surveys of these distant clusters using the SC method and spacefaring missions, we need a way to compile and verify that this data is reliable and statistically significant. This is where the halo mass function comes into play. In order to do precision cosmology, we need cosmological simulations. It's theorized that gravitational instability early in the universe formation leads to clusters of dark matter halos. Early forms of calculating halo abundance were useful in getting us to where we are now, but unfortunately were not accurate or detailed enough to be used with different redshifts and varying cosmological parameters. Now we have the computational power to run full-scale simulations. There are two ways to observe and collect data of dark matter halos. One is using the overdensity method, which entails simply setting a threshold of densities and surveying the regions with densities that surpass this threshold. The threshold is typically set to the critical density of the universe. The dark matter halos are then identified as a spherical mass with average density delta P. The downside of this method is that it runs the risk of oversimplifying the shape of dark matter halos, incorrectly assuming that nonlinear gravity still acts in a spherical shape. Another method is to apply the friends of friends algorithm, which groups neighboring particles according to the distance between each other. This gets rid of the problem in assuming how dark matter halos act, and the shapes that come from these simulations vary in sphericity and shape. The downside of this method is that we can't really calibrate this method to observational results, and the algorithm may group halos that otherwise would not have been grouped. The halo mass function is simply a measure of the number of dark matter halos in a given region with any particular mass. The function can be expressed in a differential form or a form that emphasizes number density. The function shown on the page is the simplest form describing the differential mass function, where f of sigma describes random walks on the barrier between collapsed and uncollapsed regions, and sigma represents the threshold for overdensity for collapse. The other variables present in the function are parameters to be determined by the simulation, which demonstrates the halo mass function's universality. These two graphs are made by our research group, plotting number density against mass. But what are the limitations of these cosmological simulations? Although we do have the technology to run and detect halo mass clusters, the processing power required to run these is unfeasible for an extended period of time. My project was to find a way to sample the mass function against redshifts and mass without being too computationally expensive. My journey with the research began with learning the fundamentals of Python and utilizing CAM, a cosmology code for calculating CMB, galaxy count, and various other modules. I was first tasked with making a 2D contour plot that displayed the relationship between number count, mass, and redshift. The first plot is a contour plot of the mass function. As you can see, the function is pretty steep. So then I graphed it logarithmically to have a clearer picture. My next task was to now find a way to randomly sample a distribution. To get there, I had to learn how to sample a regular Gaussian distribution to test if my code worked, and then was able to plug in the mass function to see what results come from there. I can definitely say there was a learning curve in understanding how Python works, and that many things that work in a mathematical sense may have to be expressed differently in order to Python to understand what I wanted to do. As of now, I'm still tinkering with this code to understand the mass function and its properties, and hopefully I can continue this research in the future. I really appreciate the opportunity I was given to explore fields of cosmology and computational physics that I would otherwise not have gotten a chance to encounter given our current circumstances. I originally thought that I would be more interested in theoretical or high energy physics, but this opportunity has made me more and more interested in dark matter research and the fields that surround it. I want to give special thanks to Nick Battaglia, who was my mentor and helped me throughout the fellowship and answer many questions that I had about Python. I also want to thank the Simons Foundation and the National Society of Black Physicists for putting together such an amazing research opportunity in a time where things are very uncertain. And I made a great time interacting with other fellows in the program. Being around other Black physicists and STEM majors made me feel more welcome in my field of study. And that has been my presentation. Thank you.